Okay. Good morning or good evening, everyone. My name is Samaresh Kumar Singh, and I am presenting this research paper, Security Without Detection, Economic Denial as a Primitive for Edge and IoT Defense, with Joyjit Roy and Sriharsha Anand. Both of us are senior member of IEEE. In this research paper, instead of trying to detect every intrusion attacks, we simply made every attack expensive to run. That is the idea behind economic denial of security EDS. As a quick preview, what we have achieved is this system needs to run under 12 kilobyte of memory footprint. It slows down the attack between 32 to 560 times. Cost asymmetry ratio becomes 29,000 to 1, and combined mitigation is 94%. Let's move to the next slide. So here are the presentation outline. In this presentation, we will talk about problem statement and motivation, EDS system architecture, the four EDS mechanism, game theoretic foundation, experimental evaluation, a real malware validation and comparison, and finally conclusion and future work. So this is the problem statement. Detection-based security has three fundamental failures in IoT and edge environment. First is the encryption and stealth evasion. A modern attack doesn't announce themselves. They use encryption channel, polymorphic malware, and deliberately stay invisible. Signature-based intrusion detection is completely blind to roughly 70% of the real-world attack traffic. Second one is the resource gap, and this is the critical one for IoT. Machine learning idea system needs 50 to 150 MB of RAM to function. Typical IoT microcontroller has less than 512 kilobyte. That is 300 times, mismatch. Deploying ML-based detection on the edge hardware is not configurable, and it is a big challenge. Third one is the zero-day blindness. Every detection system depends on knowing what an attacker looks like in advance. So here is the key insights on the right side. Defender control their own environment and attackers do not. So instead of chasing detection accuracy, we exploit the symmetry and make every attack economically expensive to continue. Let's go to the next slide. So here is the EDS system architecture. This is a three-tier architecture. So let me walk you through from the top to bottom of this architecture. At the top layer, you can see the external zone here. Attackers, with the capability C1 through C7 enters from the left and legitimate users enters from the right. That is the green box you see. Tier 2 is the edge gateway, typically a Raspberry Pi equivalent to the edge server. This is a primary enforcement point for all EDS mechanism. Every incoming request first hits M1, the puzzle verifier, which introduces SAR-256 computational challenge, validated request pass through M2, a decoy orchestration, which injects indistinguishable decoy resources. M3 applies exponential backoff delay on the repeated failure. M4 pads bandwidth to amplify data exfiltration cost. As a result, most attackers are deferred right here before reaching protected assets. Tier 1 on the right side is the IoT device layer, where we have sensors, actuators, controllers. Critically legitimate users with the pre-issued certificate bypasses all puzzled computation that we saw on the left side via certificate fast path and access the protected assets directly with no overhead. The last layer, layer 3, is at the bottom is the cloud analytic layer that correlates telemetry across the sites and pushes active policy update back to the gateway. All inter-tier communication uses mutual TLS 1.3 and challenge response is stateless. That gives us horizontal scalability of 3,800 requests per second. Now I'm going to hand over to Joyjit Roy to proceed further from here. Joyjit.
Thank you, Samaresh. So now let me walk through the four mechanisms that makes EDS work. Each one attacks a different dimension of attacker's cost. So the first one, computational frictions. Every incoming request has to solve a puzzle, right? So the difficulty scale up based on how suspicious the client looks. Legitimate users with valid certificates skip this entirely. On its own, it slows attackers down by 8 times. Second is interactional entropy. So we mix a fake resources alongside real ones. The attackers cannot tell which is which without fully engaging with each other. So combined with the fast mechanism, these puzzles slow down the whole process up to 32 times. The third is temporal stretching. So after each failed attempts, the wait times doubled. So we are not blocking anyone. We are actually making it progressively more expensive in time. So legitimate users are not affected. And the fourth one is resource taxation. So we pad every responses with noise data. If an attacker tries to steal data, they have to download and process all that junk too. So in the exfiltration scenario, this drives the combined slowdown to 373 times. So the key takeaway here is these four do not just add up, actually they amplify each other. So this slide shows how EDS is not just an engineering hack, it has a solid game theory foundation. So the core idea is simple here. The defender moves fast. We set the puzzle difficulty before the attackers act. The system automatically calibrates this, so the attackers always end up spending more than their budget, right? On the right side, you can see the attackers' profiles. A script kiddie with $50 is stopped easily. A cyber criminal with $2,000 and GPU needs a greater difficulty, right? Even organized crime with $10K and 100 bots can be deferred. So, and at that level, we recommended combining EDS with the traditional IDS for layer defenses. Well, the second key result is superlinear composition. When the four mechanisms work together, the total cost to attackers is 2.1 times higher than the sum of their individual costs. So they genuinely amplify each other. And at the bottom, you see the cost asymmetry numbers. Even in the worst case, the ratio is 218 to 1. At baseline, it is like 29K to 1. That means for every dollar the defender spent, the attackers must spend thousands. That's the powerful economic deterrent. Moving to next slide. Now let me show you the result. So we tested EDS across 4 real attack scenarios on 20 IoT devices. In SSH brutal force, attacker success dropped from 62% to just 8%. So network scanning was slowed by 32 times, data exfiltration by 49 times, and command and control was slowed by 560 times, essentially killing the campaign. So I'll look at the footprint on the right side. Just 11.6 kilobytes of memory used under 20 milliseconds latency and 0 false positive. This runs comfortably on an ESP32. So the bottom line here is individual mechanism gives you 15x slowdown, but combining EDS deliver 32 extra slowdown. So that's the superlinear amplification in action. All results are statistically significant. Now I'll hand it over to our last co-author, Sriharsha.
Thank you, Joyjit and Samaresh. So to go beyond synthetic attacks, we replayed 4 real IoT malware families from the publicly available IoT 23 datasets, Mirai, Tori, Hajime, and Kojiro. This produced 600 experiments across 4 families, 5 configurations, and 30 trials each. The horizontal bars compare IDS alone mitigation in gray against the EDS mitigation in teal. EDS alone outperforms IDS across every single family, 88% versus 67% for Mirai, 59 versus 40 for Tori, 72 versus 55 for Hajime, and 92 versus 70 for Kenjiro. When we combine a EDS with the random forest IDS, mean mitigation reaches 94%, 27 percentage point improvement over IDS alone. This validates the complementarity between the two approaches. EDS imposes economic friction regardless of whether the attack is recognized, and the IDS catches what managed to slip through. The comparison table on the right puts EDS in context against rate limiting, snort, cowrie, honeypot, and RF IDS. EDS delivers a 32 times slowdown with 0 false positives and a 12 kilobyte footprint, approximately 7,000 times smaller than a typical ML-based IDS, while outperforming all of them on attack slowdown. In conclusion, so let me close with 4 key contributions. First, the unified EDS framework. The first systematic integration of 4 cost imposition mechanisms with formally proven 2.1 times superlinear composition guarantee, 32 times combined slowdown versus 15 times additive. Second, the game theoretic foundation. A Stackelberg equilibrium with a close-formed optimal solution that enables automated parameter selection on resource-constrained IoT devices, which prior game theoretic work has not achieved. Third, comprehensive empirical validation on real IoT hardware against real malware. 32 to 560 times attack slowdown, cost asymmetry up to 520 to 1, and 94% combined mitigation. Fourth and the last one, an IoT-ready production design that fits in under 12 kilobytes, adds less than 20 milliseconds of latency at conservative settings, and degrades gracefully under DDoS without dropping legitimate traffic. Looking ahead, future work includes reinforcement learning for dynamic parameters tuning, formal integration with zero trust architecture per CISA's ZTA 2.0 model, and independent red team valuation in production deployments. EDS does not replace detection. It makes attacks economically irrational before detection even becomes necessary. Thank you so much.